we present a novel outdoor virtual reality concept and develop a robust technique for headset tracking in the outdoor environment. Existing VR systems perform camera-based inside-out headset tracking relative to a local reference frame, for example, an ad hoc frame fixed to a living room. When used outdoors, they perform unreliably. Lighthouse-based headset tracking cannot be used in sunlight, and camera-based inside-out headset tracking requires well-lit conditions with a rich local visual texture so that its SLAM algorithms can extract enough visual features to reliably infer the headset's pose. We have developed a concept for outdoor VR that we call open world virtual reality, and we have built a software and hardware platform to support it. Whereas simulating self-motion in a confined indoor space can result in visually induced motion sickness, open world VR offers a mixed reality experience in which a user's self-motion is governed entirely by natural physical movement. Further immersion is possible when a high-resolution 3D reconstruction of the local environment is available and when headset tracking is precisely referenced to the local structural environment. When these conditions hold, users can transform the real world into a personalized landscape in which they explore and even touch virtually represented components of the real world. In effect, users can overlay a virtual skin of their choice on the physical world. Our platform anchors the VR headset pose to centimeter-accurate carrier phase differential GNSS. This enables continued operation in variable outdoor visual conditions and permits virtual objects to be persistently located in the real world despite radical changes in the visual scene like snowfall or construction. This paper's primary focus is on algorithms for robustly tracking the CD-GNSS-based headset pose despite signal blockage and multipath. We developed the first reported tightly coupled CD-GNSS inertial system that makes use of a smartphone-grade IMU. The headset is paired with a backpack that carries a small computer running the GNSS receiver and tracking algorithms, and a gaming laptop running the VR engine. This block diagram shows how the various system components interact. The headset houses primary and secondary GNSS antennas, whose output signals are synchronously sampled with specific force and angular rate measurements from a smartphone-grade IMU. The CD-GNSS positioning block, which runs on the single-board computer, pulls IF samples from the headset and processes these via an advanced software-defined GNSS receiver called GRID, developed at the University of Texas. The receiver and front end are capable of multi-frequency GNSS tracking, but only GNSS signals at L1 are used for the VR application so that the headset antennas can be lightweight. GRID also encompasses a specialized CD-GNSS positioning engine developed at UT that is designed for operation in urban environments. It produces estimates of the primary antenna position, accurate to centimeters, and headset azimuth and elevation estimates, accurate to a few degrees. Pose and twist estimation is performed by a signal point Kalman filter that also runs on the single-board computer. The estimator takes vector position and 2D orientation estimates from the CD-GNSS positioning engine and fuses these with IMU measurements to estimate headset position, velocity, orientation, angular rate, and gyro and accelerometer biases. A 24-state element variant of the estimator is used offline to calibrate extrinsic and intrinsic parameters of the IMU. Headset pose estimates are fed to the gaming laptop, where a plugin performs the necessary coordinate transformations so that the VR engine's rendered scene corresponds to the input pose in an absolute sense. The system's end-to-end latency from head movement to its effect on the displayed pixels is under 30 milliseconds. Data collected during a VR experience under good GNSS visibility conditions was used for an initial test of the system. In this case, a confident ground truth could be obtained against which experimental offline runs with various artificial impairments could be compared. A first check examined the size of the accelerometer and rate sensor biases estimated by the pose estimator. That these remain small over the nearly 5-minute walk with natural VR head movement indicates that the IMU, kinematics, and measurement models assumed within the pose estimator are accurate. In a more challenging test, GNSS measurements entering the pose estimator are artificially suppressed to evaluate the estimator's ability to flywheel through GNSS outages. In this case, a 3-second outage was simulated every 10 seconds over the 5-minute walk. This view of the first 100 seconds shows that the east, north, and up headset position errors, shown in dark blue, are consistent with the pose estimator's expected uncertainty, shown in light blue. The cumulative distribution function of the final error at the end of the 3-second GNSS outages shows that, when properly calibrated, the smartphone-grade IMU supports GNSS denied positioning over 3-second intervals to better than 23 centimeters. But GNSS signals are rarely completely denied in the outdoor environment. More often, one experiences blockage of a subset of signals. To simulate such conditions while retaining a confident ground truth, one may artificially suppress any number of double difference pseudorange and carrier phase measurements feeding the integer-constrained estimation engine. Consider a case in which all but the 3 strongest and highest elevation signals were eliminated in 10-second intervals with a period of 20 seconds. The pose estimator experiences positioning errors greater than 2.5 meters in this case, as the CD-GNSS engine loses its integer-constrained fix and falls back to a float solution. To address this problem, which arose often in early testing of our OWVR prototype, we modified our estimation architecture to support what we call a federated tight coupling. In this coupling scheme, the full state and covariance of the pose estimator are made available to the CD-GNSS positioning engine's internal estimator. Normally, the latter performs a time update based on nearly constant velocity and static orientation dynamics models for the headset. This works fine under good GNSS visibility because the GNSS observables, which are updated at 20 Hz, prevent errors caused by these crude dynamics models from accumulating. But under poor GNSS signal availability, the errors do accumulate, causing a loss of integer fix. If the CD-GNSS engine's internal estimator instead performs its time update by borrowing a position and an elevation azimuth prior from the pose estimator, dynamics modeling errors are much reduced, resulting in a more robust integer-constrained solution. The federated approach is admittedly suboptimal. Better would be to jointly estimate pose, twist, bias, and integer states in a combined central estimator. In the federated case, it is difficult to account for the correlation that builds up due to feedback between errors in the antenna position, azimuth, and elevation estimates and errors in the pose estimator's state. Nonetheless, a federated solution has the virtue of being easier to develop, test, and maintain. And by attenuating the claimed precision of the state estimate in the feedback link, one enters a regime in which conditioning on the integer constraints substantially decorrelates the estimates with the pose state. As a result, federated tight coupling achieves strong performance gains over the original loosely coupled architecture, as will be shown. Here is the same data set with 10-second artificial GNSS impairment events on which the loosely coupled system failed to maintain integer fixing, but now with tight coupling. One can see that vertical errors grow slightly beyond 20 centimeters in this case, when only 3 double difference measurements are available, but horizontal errors remain below 5 centimeters, and the system never loses its integer fix. It is instructive to closely examine a case in which the loosely coupled system loses its integer fix to appreciate how the tightly coupled architecture achieves its advantages. First, some discussion of the integer fixing algorithm used in our CD-GNSS engine will be necessary. Double difference carrier phase and pseudorange observables are initially screened by a combination of quality indicators to filter out signals likely to be outliers due to multipath. A float solution, followed by innovations testing, is performed on the remaining signals. Then, an integer least squares algorithm searches for the integer vector that produces the lowest cost given the prior state estimate and the current epoch's observables. The integer vector is only accepted if an integer-aperture test indicates it is highly likely to be correct. We apply a difference test with a constant failure fixing rate. If the test is successful, then our engine conditions the real valued state elements on the assumed correct integers and outputs the precise solution. Importantly, integer states are completely discarded from one epoch to the next, whether after conditioning or marginalization. This avoids the need to detect and correct cycle slipping, which occurs often in urban precise positioning. What exactly causes the aperture test to fail for the loosely coupled system under artificial impairment? Consider a case study of a hairpin turn. The true headset trajectory is shown by the blue dots. Severe artificial signal blockage is induced during the full trajectory, leaving only 3 double difference measurements out of 12 originally available. The loosely coupled system maintains a correct integer fix despite the partial outage over the first 15 seconds. But at the point indicated in the lower plot, the aperture test statistic collapses. A fixed solution is abandoned, and the loosely coupled system's errors grow to several meters as it struggles to provide even a float solution. What precipitated the sudden collapse? And how did the tightly coupled system avoid it, even when processing identical data? The collapse was caused when one double difference signal was replaced by another with unfavorable geometry, which suddenly weakened the model. One can appreciate this by examining various so-called model-based indicators, which characterize the strength of a solution from the point of view of the prior before measurements are considered. The 3 shown here all indicate a degradation for the loosely coupled system at the same time when the test statistic collapsed. Especially revealing is the lower plot, which shows a large sudden uncertainty increase along at least one dimension in the integer domain. Why was the tightly coupled system spared a similar fate? Because its prior position uncertainty was much tighter than the loosely coupled systems, providing it a bulwark against a collapse of measurement constraints. To further demonstrate the tightly coupled system's robustness, we subject it to natural rather than artificial signal impairments. An open-world VR user walks along the east wall of the UT Aerospace building, under the building's overhanging eaves. In this case, only 2 to 5 double difference signals remain available. The user spends a total of about 1 minute with a highly obstructed view and strong multipath from the building wall. In this case, ground truth is not available, but one can nonetheless evaluate system performance on various metrics. The loose architecture fails to maintain an integer fix in the degraded conditions. A gap in the data indicates a loss of fix, and the discontinuity in the top plot indicates that when an integer fix was regained, it was incorrect. By contrast, the tight architecture maintains an apparently correct integer fix throughout the test, despite the number of measurements dropping to 2. This remarkable result highlights the robustness of the tightly coupled architecture. In summary, our work has made 2 contributions. First, we have introduced the concept of open-world virtual reality. Second, we have presented the first demonstration, of which we are aware, of tight inertial CD GNSS coupling using a smartphone-grade IMU.